Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Beforehand, I'd like to introduce myself. I'm Silma, as the Master of Ceremony in this international guest lecture hosted by Industrial Chemical Engineering Department. And on the behalf of the committee, we would like to say thank you to Professor Kunihiro Fukui from Hiroshima University for coming here despite the tight schedule. It is really an honor to have you here, sir. Moving right along to our beloved lecturer, Dr. Engineering Eva Octavia Ningrum ST Master of Science, and Dr. Lailatul Komaria Sarjana Teknik will share their amazing knowledge and experience. And also, greetings to our honored lecturer and participant that has been coming here with us. And not to forget, our guest that has come in this very special occasion. Before we proceed with today's agenda, let's show our gratitude toward God that has allowed us to come here despite today's situation. Praying begin.
Okay.
Finished.
Okay.
And before we watch the introduction video prepared by the committee, I invite all the participants to open their camera and use the virtual background prepared by the committee. Okay, moving along. Please for the committee to share the video.
Okay. Can you see my slide? Can you hear me? Sorry. Can you hear me?
Surabaya, the provincial capital of East Java, is the second largest city in Indonesia. This city has a huge number of diversities among the people, cultures, and ways of living. Surabaya has been acknowledged for its green public open spaces. It also has successfully equalized the development between build-up area and green area that makes Surabaya a livable city for all.
I see Surabaya as a great city with amazing people. Living pace
Can you see
here
my
is
slides?
quite slow, so you don't feel the rush of living in the city.
It's also a good place to travel around. I mean, in bus you can go in many places, or taking
Can I
train on
start my
Java.
presentation?
It makes me so to be in peace, so I think that is a good place for me to stay.
Surabaya is also known as the City of Heroes because of its role in Indonesian struggle for independence. Moreover, Surabaya nowadays has already become the center of businesses, commerce, industries, and education in Indonesia. One of the pioneers of education in Surabaya is the Institute of Technology Sepaluna Pemba, better known as ITS. ITS has 3 campuses in Surabaya. ITS Sukolilo as main campus. ITS Manyar its campus vocational study of civil infrastructure engineering. ITS Jokro Aminoto as campus for Master of Management Technology. Occupying a large area of 180 hectares as its main campus. ITS has 20,000 students, 1,000 academic staff, 1,000 non-academic staff, 10 faculties, and 38 departments. ITS has various fields of study, faculties, and strategic study program which are the center of excellence. Faculty of Industrial Technology, Faculty of Marine Technology, Faculty of Electrical Technology, Faculty of Civil, Environmental, and Geoengineering, Faculty of Business and Management Technology, Faculty of Architecture, Design and Planning, Faculty of Information and Communication Technology, Faculty of Mathematics, Computing and Data Science, Faculty of Natural Science, Faculty of Vocational Studies. Study program at ITS consists of vocational program, bachelor program, master program, and doctoral program. ITS also has more than 130 full-time international students and 400 international student mobility short program, K&B program, student exchange, and another programs.
I work with many projects and many assignments, so it's helped me to improve my personal skill and also for communication skill.
There are many things that we have to fulfill, and ITS has been helping me to improve this kind of things. beside my hard skill, I also have been able to develop my soft skill, which is important for nowadays leadership.
Also with ITS, I had a lot of opportunities to join different events for free, like the Rujak Connect Festival, which was the cooking event, something. Yeah, this is like kind of opportunities that you don't have every day, and it's funny to take part for once, or yeah, it's nice.
ITS inventing many technological innovations that have been acknowledged in various international competitions. These are several national and international achievements by ITS. ITS Central Library is in a 6-story building, with total building area 9,000 meters square. This library, more than 121,000 printed textbooks, more than 10,000 e-books, 10,000 audio-visual data, and 18,000 digital library collections. Besides providing students with the books, the library also provides students with comfort study area, like discussion area, hotspot cafe, computer rent, multi-purposes room, and Indonesia Development Information Services, which connect to the World Bank database. Research and innovation at ITS are geared towards addressing global challenges. Therefore, creative inventions are increasingly being produced by ITS researchers.
If people are talking about logistics and supply chain in Indonesia, we publish papers, we are doing research on transportation modeling, we are doing research on warehouse modeling, and we also do a lot of networking with industries, with companies, and our research has been used in many companies in Indonesia.
We know that Indonesia is the second biggest biodiversity in the world after Brazil, but I think if we combine with our sea area, Indonesia will be the biggest biodiversity in the world. And we do believe that if we perform science of nature and how to utilize it, it is very big opportunity for the treatment of some disease, not only for Indonesian people, but also for the world.
Considering the fact that Indonesia has unique climate characteristics, and also Indonesia is also very well known as the laboratory of disaster, therefore a lot of issues, a lot of problems have to be solved. But this is a challenge for us. We cannot work alone. We need to work interdisciplinary, which involve expert, local or internationally. Therefore, we invite all of you to work here with us in ITS. We expect that our contribution and our work will bring ITS as the Center for Excellence in Disaster in Indonesia.
ITS has more than 180 laboratories spread over 10 faculties. The laboratory is used to support faculty and students' research and provides the opportunity to collaborate on big projects and create impactful research programs.
think ITS has contributed a lot in terms of giving an ideas and spirit, and at the same time self-confidence to our country about how capable we are.
ITS, within the next 5 years, it would be a research and innovative university. It means that ITS will be playing a big role in the region, especially in Asia. For the next long term, in 2045, ITS would be an entrepreneurial university. Means that it having a big role playing in the global world.
So, come and join us.
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 Come and join with us, ITS.
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 University of Heroes.
Besok jam 1 siang mau free nggak Pak? Mau saya ajak.
Insya Allah.
Ikut apa?
Assalamualaikum warahmatullahi wabarakatuh. Om Swastiastu, salam budaya, salam kebajikan.
Event apa lagi? Orang nggunain instrumen kok.
Right. Moving forward, I welcome Dr. Insinyur Nini Fajar Puspita, Master of Engineering, as the head of Industrial Chemical Engineering Department, to give an opening speech and remarks.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon for all participants in International Guest Lecture, and also our student and our department members. As we mentioned, I'm the head of Department of Industrial Chemical Engineering, Faculty of Vocation, ITS. I would like to say welcome you at International Guest Lecture 21 that organized by Pak Ahmad Vitama Karisma and Ibu Saida as a head of Applied Chemistry Laboratory and Industrial Biotechnology Laboratory, respectively. In today's International Guest Lecture, we have 3 topics. The one will be presented from Professor Kunihiro Fukui, a head of Fine Particle Technology Laboratory, Hiroshima University, and others from our department members. 2 lecturers from our departments are Ibu Dr. Eva Octavia Ningrum and Ibu Lailatul Komariah will share her applied research and her experiences in the specific fields to all participants. We hope this today's international guest lecture will give very beneficial and valuable contribution for developing and improving the productivity of to our laboratories, and also we hope it gives an impact to our industry and society. The next, we hope, if it's possible, our lecturers can make research collaboration and joint publication with Prof. Fukui. Finally, I would like to say special thanks to our guest lecturer of Professor Fukui for your sharing knowledge and research experience. Thank you so much for all participants for taking the time and energy to attend this international guest lecture. Please enjoy and discuss. Waalaikumsalam warahmatullahi wabarakatuh.
All right, thank you so much, Mrs. Nini, of the amazing opening remarks. Okay, moving right along, it is now my pleasure to introduce our moderator that will lead today's discussion. So I invite Mrs. Saidah Altway. Hello.
Yeah, hello. Thank you, Miss Silma.
All right.
Yeah. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon, ladies and gentlemen. The Honorable Professor Kunihiro Fukui, Dr. Eva Octavia Ningrum, Dr. Lailatul Komariah, Dr. Nini Fajar Puspita, and all of participants. Ladies and gentlemen, in the international guest lecture today, we have 3 speakers. And the first speaker, Professor Fukui, will share his research about the cyclone separator as the basis of classification technology and on the application of classification to the potassium enrichment of biomass combustion as. The presentation and discussion will be in 60 minutes. But before that, I will show to you all the curriculum vitae of Professor Fukui.
Okay.
Yeah. So Professor Kunihiro Fukui, the course of him is the cyclone separation as the basis of classification technology and on the application of classification to the potassium enrichment of biomass power combustion, and affiliation Hiroshima University Graduate School of Advanced Science and Engineering, Department of Chemical Engineering. His position professor and head of Fine Particle Technology Laboratory. His educational background from Kyoto University Chemical Engineering, bachelor degree, and then Kyoto University Chemical Engineering from bachelor degree until doctoral degree. And his research field, chemical reaction and process system engineering, transfer phenomena and unit operation, and also composite material and interface. Affiliate academic societies, the Society of Chemical Engineer, the Society of Powder Technology, Japan Association of Aerosol Science and Technology, and also APPIE, the Association of Powder Process Industry and Engineering. Yeah. Okay. For the first turn will be given by our first speaker. Please welcome Professor Fukui. The time is yours.
Okay. Thank you for introducing me politely. I'd like to start my lecture. Okay. Now also I will share my slide. Okay. Okay. Can you slide? Can you see
Yes.
slide? Okay. Okay. Thank you for introducing me politely. I'm very honored to deliver my lecture in international guest lecture held by ITS. I'm Kunihiro Fukui from Hiroshima University. Okay. Okay. And today I would like to present the entitled principle of the cyclone classifier and its application to the recycling of biomass combustion ash as fertilizer material.
Okay, to begin with, let me introduce myself briefly. So I have been the convener of Working Group 7 of ISO TC 142, whose name is Cleaning Equipment for Air and Other Gases. So we are now established some international standard concerning the bag filter system. Okay. And so I have been the vice president of the Society of the Particle Technology Japan since 2019. And I have also served as editor-in-chief and editor for several journals. Okay. Well, I would like to start my lecture today. First, I'd like to start by identifying the definition of classification technology. Okay. As you know, the size classification is to divide particles by particle size with using inertial force, centrifugal force, and so on. So in other words, it is to selectively collect only coarse or fine particles. The major classifiers include sieves, cyclones, electrostatic classifier, and so on. So you can see the outline of the cyclone classifier, okay? And so the light movie shows the trajectory in the cyclone, the trajectory of the particles in the cyclone, okay? So the particles swirl down to the bottom of the cone, and rises up to through the inner cylinder. And so the particles classified to parts. The larger particles is collected at the dust bin, the bottom of the cone, and the final particles are discharged from the inner tube. Okay, so this is outline of the cyclone. Oh, sorry. Okay. So as you know, the total collection efficiency and the partial separation efficiency are used as evaluation indexes for classification performance. Okay. The total collection efficiency is defined as a ratio of the amount of collected particles to the total amount of particles introduced into the classifier. Thus, which is given by this equation. And on the contrary, for powders having the dispersed type of the particles, so the collection efficiency depends on the particle size. In general, particles with larger size have higher collection efficiency. Okay, therefore, as shown this figure, the classification performance can be evaluated by the partial separation efficiency curve like this. Okay. So, which is the collection efficiency for each particle size. So this is a very important index of the classification performance. So next, I will move on to the explaining of the Cyclone Classifier. The cyclone is one of the most popular centrifugal force classifiers. The cyclone is categorized three types. So one is the tangential inlet type. Next is swirl type inlet type. And the last is the axial flow type. Okay, so the cyclone can be categorized depending on the inlet shape as this figure. The cyclone has a very simple structure. Okay, so the cyclone has no moving parts, and this is inexpensive to install and maintain, which can be used at high temperatures and high pressures and high dust concentrations. So this is a very severe conditions. So in these severe conditions, the cyclone can be used. This is a very famous characteristic of the cyclone. So next, we want to explain the airflow and the particle movement in the cyclone. Okay, the airflow in the cyclone spirals down the cylinder and the cone and reverses at the bottom of the cone. Okay, swirling and rises up to the and so discharged from the inner cylinder tube. Okay. On the other hand, particles in the airflow are separated by centrifugal force on the inner surface of the cylinder and cone. Okay, and fall into a dust bin. Okay, so the relatively larger particles can be collected by the dust bin. The cyclone is usually operated at an inlet flow velocity is equal to from 7 to 20 meters per second. And in general, as the diameter of the cyclone is larger, it is operated at a lower inlet velocity. And next, so since the actual airflow in a cyclone is a three-dimensional flow with complex secondary flow and very complicated turbulence. So it is very difficult to accurately estimate its particle motion and classification performance. However, a formula has been proposed to calculate the cut size based on a simplified model as shown in this figure. This model is called horizontal separation model. This is a very basic and simplified model. So this model assumes that the particles reach the wall and are collected by centrifugal force acting perpendicular to the flow, while the incoming airflow at inlet velocity ui rotates n in the cyclone. Okay, so this is a model. Okay, the particles is flow into the cyclone from the cyclone inlet. Okay, and the centrifugal force is acting on the particles, perpendicular force perpendicular direction for the airflow direction. Okay, and so particles moves to the outer cone or outer surface of the cylinder. Okay, so from this model, we can obtain the cut size by using this equation. Okay, so the crystal separation size, okay, can be obtained by this equation. The critical separation size means the smallest particle size which is captured at 100%. So from this figure, you can see that the cut size, the critical separation size is proportional to the root of the B. The B means the inlet wise of the cyclone. So this equation indicates that the cut size increase with the size of the cyclone. So this is a very important point of the cyclone performance. Okay. So as you can see in this table, some estimation equations have been proposed. Okay. So one is the Clift et al. Model, which is which was calculated by using the particles residence cell time in the cyclone. And another type is the Diaz method. So this method uses the dimension ratio of each part of the cyclone and the Stokes number. And another type is the empirical equation model, which is proposed by Yotzier et al. Okay, so you can see is the results. Okay, the relationship between the partial separation efficiency for the experimental and estimation results. Okay, so this plot shows the experimental results, and these three lines estimation line, approximation line, estimation line by these models. Okay, so you can see that the estimated results are not in complete agreement with the empirical result, experimental results. But they can be predicted with some accuracy, and so I think that these models are practically useful. Okay, so you can understand the basic of the cyclone. So next, I will move on to the application of the classification technology to the recycling of biomass combustion ash as fertilizer material. Okay, let me mention the background of this study. Okay, so in 2012, the government of Japan established the feed-in tariff scheme for renewable energy, which can promote the utilization of woody biomass for electrical power plant. Okay, because carbon dioxide emitted from the combustion of biomass is considered to be carbon neutral. Okay, so and the inorganic components are discharged from the power plant as biomass combustion ashes. So these ashes must be disposed for reclamation at the last disposal site in Japan. So the cost of this step should be reduced in order to promote the construction of biomass power plants. So we must reduce the combustion ash. So, and the woody biomass combustion ash can be used as a raw material for fertilizer because it consists of calcium, silicate, and potassium component mainly. Okay. So chemical fertilizer manufacturing companies can pay for combustion ash with potassium content of more than 25% as a valuable raw material. However, in general, the potassium concentration in the ash is not so high as 25%. So we must enrich the potassium component. Okay. So therefore, in our study, the existence form of potassium components and the dependence of the potassium concentration on the ash particle size should be revealed. And based on this, a factory scale potassium enrichment method by using the particle size classification technique is proposed in actual biomass power plant. These are our objective of this work. Next, first of all, I would like to explain the tested combustion ashes and experimental method. Okay. Table 1 lists the type of the furnace and fuel and potassium content in plants from A to D. Okay. So, and 4 types of biomass combustion ash samples were used as a test samples. These tested samples were obtained from various fuels, as shown in this. Okay, and so these ashes was eliminated from the different type of the furnace. Okay, the plant A has a fluidized bed type of the fluidized bed combustion ash and combustion furnace. And from B to D, these plants has a stoker type furnace. Okay, and the combustion ash from plant C has a very low potassium content. Okay. So as shown in figure 1, okay, so these are the types of these are the process of the biomass power plant. Okay, plant A is installed. Plant A is the fluidized bed furnace is installed in plant A, and plant B to D consists stoker type furnace. Okay, this is a different point of these types of the combustion ash. And next, what you can see the schematic. What you can see here is a schematic diagram of ash classification experimental apparatus of the laboratory scale. Okay. So this is experimental setup, okay? So the sample ash aerosol was introduced into the cyclone separator, okay? And the coarse ash was captured in the dust bin at the bottom of the cone. And so final ash was collected by a glass fiber filter, okay? And the cut size of the cyclone separator was controlled by the blow-up flow rate. Okay, this is the inlet of the blow-up flow. Okay, this blow-up flow was introduced from the dust bin. And then the potassium concentration of the classified ash the potassium concentration of the classified ash in order to clarify the dependence of the ash component on its particle size. The analysis methods for the analysis methods for ash properties are summarized here. So we measure the particle size distribution and potassium concentration and morphology and the crystal phase. Okay, these properties were measured by these instruments, respectively. So now I will move on to the experimental results. Okay. So figure 3 shows the relationship between the mass median diameter of the classified combustion ash and the potassium concentration for each power plant. Here, the dispersion medium of this here, the dispersion medium for size measurement was ethanol, okay? For all power plants, the potassium concentration in the ash increases as its median diameter decreases, particularly in the range of below 10 micrometer, the concentration increases rapidly. However, the dependence of the potassium concentration on the particle size is very different among the 4 power plants. Namely, we can say that the ash from plant B has the most remarkable dependence on the particle size. So the experimental result is here, okay? So from this figure, the component of the fly ash depend on the particle size. Next, in order to confirm the aqueous solubility of the potassium component, the ash was completely washed by distilled water. Xrd peak patterns of the original and washed ash from plant A are shown in this figure. Okay, the left figure shows the crystal structure of the original ash, and the right figure shows the crystal structure of the ash after washing. Okay. Xrd peak patterns of the original ash contains the crystalline phases of CaCO3, KCl, K2CO3, and K2SO4. In contrast, concerning the ash after washing, the peaks of CaCO3, only these peaks can be observed. So peaks of potassium components disappeared from washed ash. So peaks due to CaCO3 was only observed. Okay. So concerning other ashes, the same tendency could be acquired. Therefore, these results suggest that almost all the potassium components exist as crystallized hydrosoluble materials for all types of ashes. Okay. Next, from previous slides, when distilled water is used as a dispersion medium, only particles of water in soluble component, such as CaCO3, can be measured in the particle size distribution. On the other hand, it is well known that ethanol, so the ethanol cannot dissolve any component in the combustion ash. Therefore, the particle size distribution of water-soluble particles main, and which is correspond to the potassium component. And these types can be calculated from these data. Okay, so figure 5 shows the particle size distribution of water-soluble particles component. Okay, so this is the left figure shows the cumulative undersize distribution of the insoluble component particles. Okay, which correspond to the CaCO3. And so right figure shows calculated particle size distribution of water-soluble component, which mainly correspond to the potassium component. Okay, so this is the right figure. Okay, the left figure is insoluble component. The right figure shows the particle size distribution of the potassium component. Okay, so for insoluble component, the difference in the size distribution cannot observed in the range of the below about 20 micrometer. Okay, so we cannot find the difference in the range of below about 20 micrometer. However, it can be found that the mass median diameter of soluble component, particles is remarkably different among the four types of the ash. So these size analysis results reveal that the difference in the dependence of the potassium concentration on the ash particle size among power plants shown in previous figure is due to the variation in the size distribution of soluble type of the potassium component. Okay, so to investigate the form of potassium component in the ash, SEM observation of original ashes and their elemental analysis by EDS were conducted. The results were shown in these figures. These figures reveal that the potassium component in ash, this is a particle 2. So this particle 2 consists of KCl. Okay, so the potassium component in the ash exists as single KCl particles, so having about 3 micrometer in diameter, okay? Which is almost the same size as a spherical CaCO3, okay? These particles consist of only CaCO3. So, the same analysis of another ashes at higher magnification was also carried out. So you can see the summary about the form of potassium component in the ash in table 2. The obtained size of potassium component particles by SEM-EDS analysis are in qualitative agreement with that measured by the particle size analyzer, which are all relatively smaller than the original ash. So, okay, so the particle size of the potassium component measured by SEM-EDS is around lower than 6 micrometer and so on. So this value is almost the same as the calculated ones. So the data was here. So the size is around about single micrometer. So the particle size is almost the same between two types of the measurement. Okay. So some components of the crystalline phases identified by Xrd measurement are also detected in SEM-EDS analysis. Okay. So accordingly, these experimental findings lead to the conclusion that the potassium component in the combustion ash mainly exists as relatively small using small single particles of crystalline potassium components. Although the particle size is different, okay, the particle size is different, okay, okay. Okay, so for this reason, the potassium enriched ash can be obtained by collecting the finer ash selectively using a particle size classifier. Okay. So next, we want to evaluate the enrichment factor. Okay. Figure 11 shows the relationship between the mass median diameter of the classified ash and the enrichment factor, which was defined as a ratio of the potassium concentration in the final ash to that in the original ash, obtained by this equation, okay? So for all power plants, the enrichment factor increases, okay? Enrichment factor increases as its median diameter decreases. However, the particle size dependence of the enrichment factor was also different among types of power plants. Therefore, it can be thought that the enrichment factor depends on the three variables. So one is the potassium concentration in the original ash. And the second is the size distribution of the potassium component particles and the cut size of the classification. So I would like to discuss about the calculation method of enrichment factor. So when the cumulative size distribution of potassium component particles and insoluble component particles is given in figure 12, like this, okay? So in this figure, it is assumed that both component particles are completely classified as a particle size DPC. Okay, this is a cut size of the classifier, which means that all ash particles smaller than DPC were collected as enriched potassium finer ash. Accordingly, the value of cumulative size, so Fk DPC and Fin, F insoluble DPC, so that these are these points, okay? Now, this value can be calculated from the size distributions. Hence, the enrichment factor can be obtained by these equations, this 1 and 2, okay? So we can obtain and we can estimate the enrichment factor with using the particle size distribution as the cut size, okay? So from this simplified model, we have calculated the enrichment factor, so some model cases. So figure 13 so shows calculated enrichment factor as a function of two variables. One is the potassium content, okay? One is the potassium content. And so the another variables is the cumulative undersize value of water-soluble component particles at DPC, okay? So here, DPC were assumed to be 4 micrometers, okay? So from this figure, it can be found that enrichment factor increases monotonically with increasing the cumulative undersize value of potassium component particles and decreasing potassium content in the original ash, okay? So from this model, we can calculate the enrichment factor of the ash discharged from plant A to D. Okay. So the comparison between the measured enrichment factors and those estimated by this method for 4 plants is shown in this figure 14. Okay. The left is experimental data and the right is calculated results. So the calculated enrichment factor does not quantitatively agree with the measured values. However, since the difference in the enrichment factor among the 4 plants can be qualitatively reproduced by the calculation results, so I think that this method was considered to be effective in practical use, okay? So next, we investigate the factory scale enrichment of the potassium component. So next, we investigate whether enriched potassium combustion ash can be acquired by selectively collecting small ash particles using the factory scale classification operation, okay? So you can see the process of the enrichment. You can see the schematic diagram of the enrichment process set up in plant D. which has 18,000 kilowatt power generation capacity. Okay, this is this is original biomass power plant facility, and so we added the this enrichment process to the original biomass power plant. Okay, so all discharged combustion ash is classified by this classifier. Okay, so this classifier is mechanical centrifugal type classifier. So this is a very high performance classifier. Okay, so next, you can see the photograph of the enrichment process. Okay, this enrichment process consists an ash receiving hopper. Okay, this is receiving hopper. Okay, and so this process has feeder and disperser and high performance classifier and bag filter. Okay, and so the specification of the furnace and the boiler system are listed in this table. Okay, the classified fine ash particles were collected in the bag filter system. Okay, so this is the enriched potassium ash. Okay, and the cut size of the classifier was easily varied by changing the experimental conditions listed in table 6. Okay, so with using this factory scale plants, we investigated the possibility of the enrichment. So, and figure 17 shows a relationship between the median diameter of classified ash and enrichment factor. Okay, so the enrichment factor rapidly decreases with increasing mass median diameter. Okay, then it decreases more gradually. Okay, so and the yields at here, okay, yields at here point is equal to 70.2%. Okay, so from this figure, so we can obtain the ash having a potassium concentration is about around 300 milligram per gram. Okay, this is about the 30%. Okay, which is higher than 25%. 25% is threshold bought by the fertilizer manufacturer. Okay, so this value is more than the threshold of this 25%. Okay, and so we can obtain the ash over the 25% potassium concentration. So at those yield is about around 17%. Okay, so consequently, it could be confirmed that the factory scale classification operation can provide a high enrichment factor almost equal to that on the laboratory scale. Okay, finally, let me summarize my talk. The conclusions are listed here, okay? So thank you for your attention. That is all my presentation. Thank you for so much.
Yes, thank you, Professor Fukui, for your great presentation. Now we come to the discussion, question and answer session. For all participants, please raise your hand or write the question in the chat room. Don't forget to mention your name before. Any question? Maybe for all the participants? Okay, there's a question from Dr. Lailatul Komariah.
Okay, thank you for the opportunity. Hello, Fukui Sensei. I have one question. Based on your experiment about the cyclone separator, I see there is an Xrd analysis before and after. I just want to know why you conduct an Xrd analysis, because this is only separation and there is no reaction in this process. So why you need to conduct the Xrd analysis? I just curious about this. Thank you.
Okay, so so we have conducted.
Thank you, Dr. Lailatul. Maybe Professor Fukui.
Okay, thank you
Can
for
answer the question.
Thank you. Yes.
Please.
Okay, thank you for your question. So we have conducted the Xrd measurement for the identifying the crystal structure of the ash, original ash, and ash after washed by water. So the fertilizer has two types of potassium component. One is the insoluble type potassium component. Another is water-soluble potassium component. Okay, and so we must discuss about only the water-soluble potassium component. Okay, the water-soluble potassium component is very important for the fertilizer. So insoluble potassium component cannot be used effectively for fertilizer. Okay, so we must investigate about the crystal structure of the potassium component in the ash. So we have conducted the Xrd measurement. Okay, and of course, the amorphous component of potassium can be also soluble, also solved to the water. So we cannot measure the amorphous type of potassium component. Okay, so we must discuss about the amorphous component of the potassium component. So this is a future work. Okay, thank you for your question.
Dr. Laila, is there any question again, or it's enough?
I just summarize what you say, Professor Fukui. So you conduct an XRD analysis to make to know the composition of the original, and then after washing.
Yeah.
Okay. Okay, it's enough from me. Thank you, Professor Fukui.
Yeah, thank you.
Okay, there's one question from Puji. I have a question about the dispersion medium. Why do you use ethanol, not methanol, for example?
Your question is that why I use the ethanol as a dispersion medium for the particle size analysis. Okay. Okay, so of course we can use the methanol for the dispersion medium for the particle size analysis, but in Japan the ethanol dispersion medium is more popular than the methanol. Okay, and so we must measure the original particle size of the ash. So the dispersion media, should not be should not solve any component. Okay. So the ethanol cannot solve any component of the ash. So we use the ethanol for the particle size analysis. Okay. Maybe I think that methanol maybe can be also used, but methanol as a methanol dispersion medium is not so popular for the particle size analysis in my laboratory. Thank you.
Yeah, Puji, you can unmute your microphone if you have any question. Or it's enough? Yeah, okay. For the other participants, you all can raise your hand or just write down the question in the chat room. Professor Fukui, I have one question about maybe the economical analysis of the, because in this in your research you use cyclone, and then you add for the enrichment process you add the high performance mechanical centrifugation.
Yeah.
What is the, or how is the economical analysis of this process compared to the other separation method, maybe with the electrostatic precipitation. Yeah.
Okay, so of course the cyclone is the viewpoint of the economy. So we had better use the inexpensive classifier, so such as cyclone. So in this case, the performance of the cyclone is not enough for the enrichment of the potassium component for this combustion ash. I explained at initially, the cyclone, the cut size of the cyclone increase with the size of the cut size of the cyclone increase with the size of the cyclone. So we must treat the large amount of the ash. We must use the large scale cyclone. So in this case, the cut size of the cyclone is so large. So we cannot use a cyclone in the factory scale. So increasing the amount of the treatment capacity, we must use the multi-cyclone. So, but this is relatively expensive. So in this case, we use the mechanical type centrifugal classifier. Of course, this mechanical type is also expensive. So in order to reduce the cost, we must we had better use the simple classifier such as cyclone. But as you proposed, the electrical precipitation type classifier is also expensive. So we select the mechanical type classifier. But in future work, we must reduce the cost of the initial process of the enrichment process. Thank you.
One question, please.
Oh, yeah. Okay, from Professor Suprapto.
Thank you, Professor. According to figure 7, it's about same for biomass incineration ash, and then table 3, existent form and particle size of potassium component in ash. I have one question, please. According to dispersion medium about ethanol or distilled water, is it corresponding table 3 according to dispersion medium, please? Ethanol or distilled water, please. Thank you very much.
Yeah, and so we can measure the original. We can measure the particle size distribution of original ash. So with using the dispersion medium of the ethanol. So because ethanol cannot solve any component of the ash. And on the other hand, with using the dispersion medium of the water, so the water soluble component is disappeared, so we can obtain the particle size distribution of the only insoluble component. So we calculate, using these types of data, the particle size distribution of the insoluble component and the original ash, so we can calculate the soluble, we can obtain the particle size distribution data of soluble potassium component. So we cannot measure the particle size distribution of potassium component directly. So we have used the two types of the dispersion medium. Thank you.
Thank you very much, Prof. Fukui. It is completely research and result, and also the reasoning of its result. Thank you very much.
Thank you.
Yeah. Is there any question?
Lanjut mungkin ya. Lanjut.
Okay, I think it's enough for the discussion session. Next, before we next to the second speaker, I will make a conclusion for this session from Professor Fukui lecture. So biorenewable energy can promote the utilization of woody biomass for electric power generation. The inorganic components are discharged from the power plant as biomass combustion ash. The combustion ash can be used as the raw material for making fertilizer because it consists of calcium, silica, and a kalium component mainly. So the chemical fertilizer manufacturing companies can pick for combustion ash with potassium content of 25% or more as a valuable raw material. So the objective in this lecture, the existence form of potassium component and the dependence of the potassium concentration on the ash particle size is revealed. A factory scale potassium enrichment experiment by using the particle size classification techniques is proposed in an actual biomass power plant. And all discharged combustion ash is classified by a high performance mechanical centrifugation type classifier. Enrichment potassium ash, which could be a valuable raw material for making fertilizer, could be obtained by collecting the finer ash selectively using a particle size classification process constructed in the actual biomass power plant. Okay, thank you, Professor Fukui, for your great presentation. But before that, before the next session, I will give back to the our MC, Miss Silma, for the photo session.
Okay, thank you so much, Mrs. Saida and Mr. Fukui for the amazing presentation and amazing discussion also. Okay, before moving to the next presentation, let's all take picture together.
Okay.
I invite all the participants here to open up their camera and use the virtual background prepared by the committee.
Yeah.
Maybe we'll wait for 1 minute until 2:29.
Okay.
Smile, please. Smile.
Okay, for the other participant, please open up your camera because we will be having a photo together. We will wait until 2:29 p.m. Once again, I invite all the participants to open up their camera because we will be having a photo session together with Mr. Fukui. All right, it's already 2:29. Okay, in my count, okay. All right, all smile. 1, 2, 3, cheese.
Smile.
Okay, for the next slide. Okay, 1, 2, 3, cheese.
Cheese.
Okay, thank you so much, everyone. And thank you so much, Mr. Fukui, for the amazing presentation. And please feel free if you want to leave today's meeting and continue your activity. But of course, we will be very grateful if you stay with us until the very end. Thank you so much. And for the next session, we will be having Dr. Engineering Eva Octavianingrum. Then I will give back this session to our moderator, Mrs. Saida. The stage is yours.
Thank you.
Thank you, Professor Fukui.
Thank you.
Thank
you.
Thank you very much.
Thank you.
Thank
Prof.
you.
Fukui.
Thank you, Prof.
Thank you, Prof.
See you.
See you.
See you.
Again.
Okay. Well, the second speaker, Dr. Eva, will share her research about novel thermosensitive copolymer gel for metal ions removal. But before that, I will show to you all the curriculum vitae of Dr. Eva. I will share. Dr. Eva, Dr. Engineering Eva Octavianingrum, STMS. With the topic novel thermosensitive copolymer gel for metal ions removal, affiliation ITS applied undergraduate program, Department of Industrial Chemical Engineering, position Department Secretary, lecturer of the ITS Industrial Chemical Engineering Department, educational background, ITS Chemical Engineering for bachelor degree, and then National Cheng Kung University, Chemical Engineering for Master of Engineering, and Hiroshima University, Chemical Engineering for a doctoral degree. And this is the list of her publications. So now the next turn, please welcome Dr. Eva. The time is yours.
Okay, thank you, Bu Saida. Can you see my slide?
Yes.
It's okay.
Okay. Thank you for the opportunity to speak today. And in this webinar, I would like to discuss a little bit topic regarding the novel thermosensitive copolymer gel for ion removals. And this is the introductions. As we know that in Indonesia, the mining company is become the second largest of the income after the agricultural sectors. Also, the production's activities are related to the environments that will have a bad impact into the surrounding mining area. Besides the mining activities and mining materials, manufacturing industries become the dominant contributor of the pollutants. Most of them include heavy metal ions that will endanger to the living environments. living environments, and biota, and also human body. Therefore, they must be treated prior to discharge. There are several cases of the pollution, environmental pollutions in Indonesia resulted from the mining activities. One of the example is the Buyat Bay pollution case in 2004, resulted from the operations of PT Newmont Minahasa. PT Newmont Minahasa is the second largest gold mining in Indonesia. And these issues has become not only national, but also an international issues. As much as 2,000 tons per day waste mining or tailing has been dumped and wasted to the Buyat Bay. They inform not only liquid and also solid. This liquid and solid pollutant have a negative impact. For example, for solids, they can bury on the basic oceans and also deposit in sediment and remain inert. Meanwhile, for liquid pollutant, they remain accumulated on marine biota and cause a disease on citizens around. Based on data, 80% of Buyat Bay people suffer disease from these pollutions. The following is the data concentrations of metal in biota taken from Buyat Bay, compared with the threshold from Indonesian national standards number 7387/2009. It can be seen that heavy metal ions such as mercury, arsenic, copper, and lead, the concentrations exceed the permitted limit of the national standard of SNI. Recently, there are several technologies that have been developed to remove and separate heavy metal ion from solutions, such as precipitations, ion exchange, reverse osmosis, nanofiltration, and adsorbents using solid such as from biomass and also by utilization of adsorbent from the gels. From the literature, it can be seen that the adsorbents is become the best technologies to remove heavy metal ion because of their environmentally friendly, not produce secondary waste, low operational costs, and they can be dissolved and can be regenerated. That's why the adsorbent gel become the promising type of the adsorbents recently. The Xrd ionic betaine is one class of the adsorbent gels. The Xrd ionic betaine polymer or gel are divided into three main groups. The first one is Carboxy Betaine. Carboxy Betaine is very soluble in water. They consist of positively charged quaternary ammonium and also negatively charged carboxylate and separate by number of methylene spacer. The second class is phosphobetaine. Phosphobetaine also separate by number of methylene spacer, separate their phosphate and also ammonium quaternary. And the third one is carboxy betaine. Carboxy betaines, they consist of negatively charged sulfonate and also positively charged quaternary. Sulfobetaine also can be defined by their methylene spacer number 3 is methylene such as N-methylene dimethyl acrylamidopropyl ammonium propan sulfonate, and for methylene spacer is butan sulfonate. In our study, we employ sulfobetaines, DMAPS, because of their facile synthesis, stable in adsorptions, less influenced by pH, and also they show thermosensitive properties in aqueous solutions. This slide shows the characteristic of poly-DMAPS. TMAPS can be formed in polymers and also in gels. If we want to make the gel, we can add the crosslinker into the solutions. And the above figure shows the transition temperature of the poly-DMAPS. The DMAPS has upper critical solution temperature. Upper critical solution temperature is the transition temperature at which below the lower temperature they immiscible in the water. However, with increasing temperature, they miscible in the solutions, especially waters. As we can see that at lower temperature, the polymer solutions, they show milky weight because the polymer form an aggregate. With increasing the temperature, the transmittance reach to almost 100%, and the solution shows transparency. The transmittance of the poly-DMAPS also depend on the concentrations of the polymers. One of the unique properties of the DMAPS polymer is their ability to form interchains, intrachains, and also intragroup interactions. Moreover, the fragment also can simultaneously absorb cation and anion because they're they having a positive and negatively charged in the same repeating unit. In our first study, we employ and apply the Xrd ionic sulfobetaine homopolymer as metal ion removal. As we can see that in the first feature, we correlate the adsorption amounts of ions. In this case, we use divalent ions, zinc, and correlate with a swelling degree. In this feature, we also use various concentrations of MPAA as crosslinker concentrations. As we can see that interesting correlations can be seen because the data point falls on the same lines without concentrations or temperature or number of concentrations of the solutions. As we can see that with increasing zinc nitrate concentrations, the absorption amount is also increased. At lower swelling degree, up to 5, they remain unchanged and decrease gradually with increasing swelling degree if we increase from 5 up to 15 swelling degree. By converting the swelling degree to polymer concentrations in gels, by using this term, we can use the second graphics. It can be seen that from 0 to 180 gram per liter, the absorption amount of zinc ions increase gradually and remains unchanged with increasing polymer concentrations higher than 180. The remaining absorption amount can be explained due to higher polymer concentrations. The association is quite strong and dominated by the intragroup association and also intrachain associations. Oh. I'm sorry, there is a lag in my slide. Do you see it move to the next slide? Not yet.
Not yet.
Okay. Can you see my slide? Feature 2?
Yes, already.
Okay. Besides the divalent solutions, we also study the effect of anion species on the relationship between the absorption amounts and the swelling degree. In this case, we use the halide solutions. Why we use the halide solutions? Because the halide solution, they have a unique characteristic. They have a different anion size and also hydrogen energy. From the feature on the left side, we can see that in Ki solution, potassium iodide, the similar tendency was also obtained. The absorption amount remained unchanged, and when the swelling degree reached around 30, they decreased significantly. This swelling degree higher than that of in zinc nitrate solutions. With decreasing the anion size in solution KBr, the absorption amount was also decreased. And for Kf, the value is almost 0. When we see this feature, we can also convert to the polymer concentrations. We can see that the absorption amount remain unchanged for Ki, almost 31 gram per liter, and KBr increased to 70 gram per liter, and for KCls up to 111 gram per liter. Sorry, Louis. I cannot move my slides. I don't know why. Sorry. Okay, this slide shows the effect of carbon spacer length on the absorption amounts. In this study, we compare between the different carbon spacer length between methylene quaternary ammonium and also sulfonate. We use DMABS and also DMABS. As we can see in the first features on the left side, is the absorption amount of cation remain unchanged. In case of methylene space, in case of crosslinker, 30 millimolar. However, if we reduce the crosslinker concentration to 10 millimolar, the absorption amount of cation decrease gradually with increasing temperature. When we compare the DMPS on the left side with the DMPS on the right side, we can see that a little bit absorption amount can be achieved by DMABS. This can be explained due to the interchange separations increases with increasing chain length of the charged functional groups. Results in enabling a greater absorption ability. As I explained previously, that the absorption ability of DMABS homopolymers is only reached 0.03 millimole per gram per liter. And also for Ki, the highest number of absorption amount is only 0.49 millimole per gram. That is only 30% using sulfonate content to interact, and that value is very low. Even we increase the concentration of the solution up to 100 millimole per liter. This can be explained due to the DMABS. They still exhibit inter and interchange association that will reduce the ability of gels to absorb the metal ions. The phenomena can be explained as follows. Xrd Betaine polymer chains have positively charged and negatively charged, and they neutral charged because they tend to interact each other to form interchange. Interchange is interaction between the different macromolecule. The interchange is the interactions in the different macromolecule, but different repeating unit. However, for intergroup is the same repeating unit. When we immerse in the solutions, for example, HCl or others, these negatively charged and positively charged, they will form a bridge, interbridging, and also interbridgings. Although they can interact the ion from solutions, the intragroups we cannot eliminate. That's become the drawback of the homopolymer if we use only the MAPS without copolymerizing with other monomer. That's why in the second study we try to copolymerize the NIPAMs with the MAPS. We expect that with copolymerization between the MAPS and NIPAM, the NIPAM will fill the space or make a distance between the MAPS, so their interactions between each other will be reduced. As a result, can increase the absorption ability of the polymer or gels. NIPAM is the most studied of thermosensitive polymer. These NIPAM have LCSD. This is different with the MAPS. The MAPS have UCSD upper, but NIPAMs they have LCSD, lower critical solution temperature. The lower critical solution temperature of NIPAMs is 32 Celsius degree. At temperature polymer below the LCSD, they will swell because their nature become hydrophilic, result from their polar groups. And when the polymer or gels, NIPAMs, condition is above the temperature above the LCSD, higher than 32 Celsius degree, they tend to shrink because their hydrophobic nature of the NIPAM itself. Firstly, we study the effect of polymer concentrations on the LCSD of poly-NIPAMs copolymerized with the MAPS in the solution of chrome nitrate. Why we use the chrome nitrate? Because the most ions consist in the electroplating is chrome nitrate. We compare between two polymer concentrations. The left hand side is only 1 gram per liter, and the right side is 10 gram per liter. As we can see that, with increasing NIPAM concentration from 80% to 100%, the UCSD of and the LCSD of this copolymer, they tend to decrease. We can also the same tendency in polymer concentration 10 gram per liter. They also tend to decrease, and the value is lower than that of 1 gram per liter. The tendency to reduce the LCSD because the hydrophobic nature of the NIPAM, because in this synthesis we use a higher concentration of NIPAMs. So the characteristic of the polymer is dominated by the NIPAM characteristic than that the MAPS. And we also try to correlate the LCSD of the polymer with the contact angles, water contact angles. This figure shows the contact angle created at the interface of the polynipom polymerized with TMAPS and the water droplet at various temperature and also various nipom concentration from 80 to 100%. As we can see that there is red dashed lines. It denotes the temperatures at which the hydrophobicity appears. As we can see that the contact angle, the left contact angle shows lower than 90 degree. However, at right hand side is higher than 90 degree. This can be concluded that at conditions, at temperature condition higher than its LCST, the contact angle tend to higher. That means more hydrophobic. Beside the contact angle, we can also see the different color. The different colors can be seen at lower contact angle. They tend to show the turbid, and higher contact angle tend to transparent. The transparency and turbidity and also color the droplets is related to the interaction between the water on the water droplet and the polymer beneath them, because over time the polymer infiltrate into the water droplets, and at some point they exceed the polymer concentrations at phase transitions. As a result, the turbidity appears. Okay. I'm sorry. The figure 6, it shows the chrome adsorptions of the polynipom copolymerized with TMPS gels in various temperature adsorptions and in various ratio between nipom and TMPS. As we can see that lower temperature result in higher adsorption ability of the ions. However, with increasing the temperature of the adsorptions, the absorption amounts tend to decrease. This can be explained to do at higher temperature, the thermal motion tend to break the association between ions and also the positively charged and negatively charged from the MAPS. So the best temperature to have a higher absorption amount is at a lower temperature. However, we have to know how they behave in their form in gels. On the right side is the swelling degree of the gels in 30 Celsius degree and 70 Celsius degree. Initially at a lower ratio of nipom, they tend to remain, but decrease gradually with increasing the nipom concentrations. Why they decrease? Because as I explained previously, that the higher nipom concentrations, it will dominate the characteristic of the polymer, because we use the nipom higher than the MAPS. The behavior is dominated by the characteristic of nipom, that is shrinks at higher temperature and swell at lower temperature. From the absorption behavior, we compare our study, especially on the absorption capacity towards chrome ions compared to other adsorptions. As we can see that the absorption capacity of our copolymer is Number 2, after zirconium dioxide loaded with composites. Their surface area, I'm sorry, we do not investigate the surface area. However, the pH is remain neutral and the concentration is quite high. If we compare the relationship between the polymer and the gels, the characteristic of the gel can be seen by the swelling degree and also ion adsorptions. However, the characteristic of the polymer can be seen by the visuals, contact angles, and also LCST. As we can see here, it was found that with increasing the napalm concentrations, when we synthesize the copolymer, the LCST tend to decrease. And however, the contact angle tend to increase. The increasing contact angles means that the polymer is hydrophilic and show transparent, as I explained previously. And how about the swelling degree? The swelling degree show the higher at lower napalm concentrations. This can be explained to the napalm is the desorption agents. Napalm is neutrals and the MABS have a positive and negatively charged. The higher negative and positively charged, the higher the absorption's ability and also the swelling degree. Because of the limitation of the usage of the MBS, even though we already copolymerized with napalms, we cannot still eliminate the entanglement between the polymer. And that's why in the next study, we try to develop to synthesize the anionic gels and cationic gel separate, and finally we blend them together in certain amount of blending ratio. In this study, we expect that with separate between cation and anion, the entanglement will not occur in the solutions. As a result, they can higher the absorption ability. And the applications of napalm acrylic acid, we use acrylic acid as anion charts and chitosan as cationic charts for the removal, ion removal, for the application of metal ion removals. Chitosan is the second largest polysaccharide after cellulose. They have group amines and hydroxyls. When they deprotonated, they have cationic charge. So they will interact with the anion from the salt solutions or the solution from wastewater. However, acrylic acid, the structure is shown in the figure above. When they deprotonated, they act as anionic, and they will interact with cationic ion from the salt solutions. It is expected that if we blend the anionic and cationic together in certain number, for example 15, we can get the environmental friendly, the higher absorption ability. They can desorb because we use napalm. Napalm have the ability to absorb, desorb the metal because their ability to shrink and swelling. And we can also obtain the reversible. Reversible means we can use not only one time. Our expectation is more than 5 times usage of these gels. The SAM's analysis shows the morphological structure of the napalm coacrylamide and napalm copolymerized with chitosan before they blend together. As we can see that in various synthesized conditions from 10, 30, 50, and 70, the more porous form in the gels. The porous structure also obtained in the napalm co-chitosan with increasing temperature of synthesis. The higher or the bigger porous can be occurred because when we synthesis at higher temperature, the napalm tend to shrink. That is condition is immiscible. So that's the gels, the form gels, and to pour and aggregate. And this shows these adsorption properties of various temperature. Our expectation that when the gels is synthesized at higher temperature, they form a lot of pores. They will increase the absorption properties. However, as we can see in these slides, actually they're not show the higher absorption amount compared to lower temperatures. The lower temperature remains have the higher absorption compared to higher temperature. In case of ferrinitrate and also nickel. However, if we compare the absorption properties of cation and anions and we blend together, the absorption of ions increase up to 5 times compared to sweater ionic gels, especially homopolymer. Homopolymer is only 0.03, and copolymerization with napalm can reach to 0.07. However, separate synthesis between anion and anion and cation can reach up to 1.3 millimole per gram gels. And finally, the conclusions of our study is polynapalms and also cationic and anionic gel were successfully synthesized in our study. And FTIR and NMR analysis confirm the successfully of the copolymerization between this constituent monomer. And the ion adsorption test confirmed that the copolymerization of napalm with TMLPS increased the molecular distance and weakened the interaction between TMPS charge groups, that is sulfonate and quaternary ammonium, leading to enhanced ion adsorptions. This observation suggests that using a lower concentration of TMPS via its copolymerization with napalm is more efficient than that using poly-TMPS homopolymer gels. Ion absorption by anionic napalm acrylamide gels blending with napalm chitosan gels is higher than that copolymerization between napalm and GMPS as a result from the reductions of chains entanglement and also chains associations. And finally, blending between anionic and cationic gels has the potential to become a new reversible adsorbent that can increase the adsorptions of heavy metal ions, low cost and also environmentally friendly. That's all my presentation. Thank you for your attention.
Okay, thank you, Dr. Eva, for your great presentation. Now we come to the discussion, question and answer sessions. So for all participants, any question? Please raise your hand or just write down your question in chat room. Dr. Eva, I have a question.
Okay.
Why you choose blending Nipamco chitosan and also Nipamco acrylic acid for the adsorbent? Have you also compared with other materials?
Yes, as I explained previously, can I share the slides?
Yeah.
Actually, from the absorption properties, it reached up to 0.1 millimole per gram gels. If we compare to other adsorbents, the polynipam 0.007, the absorption capacity reached 185.3. I believe that with copolymer with blending anionic and cationic, the absorption capacity must be higher than this value. The highest value of the adsorbent, especially for chrome ion, is from the zirconium loaded with monomer composites. The absorption capacity is around 172. So I believe that the blending between anion and cation become the promising adsorbent, which show the higher absorption capacity.
There is, I mean, what is the adsorption capacity for the blending? It's still in this, I mean, it's still studying, or there is?
Yeah, we still study.
Okay.
Study. We haven't finished the experiment yet. We only
Okay.
have the data for Fe and nickel.
Okay, but you expect that the adsorption capacity will be higher than
yeah, I expect the absorption capacity higher because then there will be no entanglement form before the blending, because they we synthesize separate between them, so they will not interact and they will not try to neutralize before we blend and immerse in the solutions of wastewater.
Okay, so until now, what kind of result that I mean that you can convince us that it will be higher? I mean in quantitative value, for example.
This one, the absorption ability.
Yeah, quantitative. Yeah. Okay.
This one.
Okay.
1.2. This is 5 times compared to homopolymer of DMA PS.
Okay. Yeah. Thank you.
Yeah, you're welcome.
For all participants, yeah. Dr. Lailatul Komaria, maybe you have any question?
Okay, thank you for the opportunity. I just have one question. Instead of adsorption application, is there any another application for your polymer, maybe for membrane or another application?
Actually, the application of the gel is quite broad. For example, for double network gel for anti-fouling activity. For example, in blood clot applications, if we offer with the betaine gel, it will reduce the fouling activity. And maybe the other example for coating in the marine ship, they use sulfobetaine usually to reduce the scaling by iota on the surface of the ship.
Okay, and then for this research, what kind of ways that you apply for your material? Is there from the industry or?
Yeah, actually our focus is on the tackle the industrial wastewater from the, for example, chrome nitrate, or from manufacturing industries, maybe electroplating or others we can use. However, before we use in the applications, we have to study the behavior of these gels in each of solutions, because we have to compare. Because in the wastewater, they have a different kind of ion. So before we choose to apply into the different ion, we have to study the competitive adsorption between each of ion. For examples, the blendings is immersed in the zinc nitrate or nickel nitrates. And after we get the data, we compare with the, for example, blending between zinc nitrate, nickel nitrate, and also chrome nitrate and other. And after that, we can compare with the wastewater, because there will be the competitive absorptions before and after blending of the solutions. So we have to have the baselines of the absorption ability of each solutions.
So maybe one question again. So this material is specific to some iron, or it just only for ferrum or nickel?
Actually, we can make it specific, but the name is not gel, but imprinted gels. But in this case, it's not specific.
Okay, so any kind of
any kind, but specific on the maybe divalent or trivalent ions we still can use. But however, we can modify it to make specific by making it imprint gel. Imprint gel, that means once it adsorbs, they release, but they absorb again in the same ions. That is imprint gels. We haven't studied yet because this study haven't finished.
Okay, thank you. Nice answer.
You're welcome.
Is there any question? Okay, from Aldi Nugroho.
Okay, thank you for the opportunity. Let me ask. I saw earlier that the absorption gel technology is very easy to regenerate. Then how to regenerate the copolymer gel with this when it is saturated? Thank you.
Oh yeah, thank you for the questions. Interesting questions. Because the gels, I stated previously, it can reversible. We can regenerate and also dissolves. We employ the NIPAM because NIPAM is not ionic gel. The NIPAM is neutral gels. The NIPAM have the hydrophobic nature and also hydrophilic nature. By switching the temperature, the characteristic of the gel, we can change from the hydrophilics. When they hydrophilic, they swells. That means the ion from the gels is interact to the solutions from wastewater. And when we change the temperature, they can also shrink. The shrink, that means we give the like force to make the gels not decrease the gels to dissolve of the ions. And about the saturated, we already studied for TMAPS to NIPAM, they can use up to 5 times. This will become an advantage because when we use the adsorbent, especially solid, we cannot regenerate. That's one of the main point of this study. Of course, we need to elaborate more in the acrylic acid and also chitosan. We haven't experiments.
Okay, thank you for the answer, Dr. Eva. That's enough for me.
Yeah, thank you.
Okay, is there any question? Yeah, okay. I think it's enough for this session. Before we go to the next session for the third speaker, I will give you a conclusion from Dr. Eva topic. Yeah, so the Buyat Bay pollution case result from the operation of PT New Mount Minahasa Raya, which has become not only national but also an international issue. In this study, it was investigated Zwitter ionic betaine polymer gel for metal ion removals. Zwitter ionic betaine polymer gel are divided into three groups: carboxy betaine, phosphobetaine, and sulfobetaine. In this research, it was used sulfobetaine because it is a facile synthesis, stable in absorption, less influenced by pH, and shows a thermosensitive properties in aqueous solutions. In this research, it was also studied the application of the Zwitter ionic sulfobetaine copolymer NIPAM DMAAPS gel as metal ions removal to minimize the drawback of sulfobetaine, and it showed a good result. Then the application of NIPAM-CoAA blending NIPAM-Co-chitosan ionic gel as metal ions removals was also investigated in this research, and the result is blending NIPAM-Co-chitosan and NIPAM-Co-acrylic acid has the potential to become a new reversible adsorbent that can increase the absorption of heavy metal ions, low cost, and environmentally friendly. Okay, thank you, Dr. Eva, for your presentation.
Thank you.
Yeah. And we will directly go to the next speaker. So the next speaker, the third speaker, is Dr. Lailatul Komaria. She will present about, she will share her research about controllable silica particle for various applications. But before that, I will show you the curriculum vitae of Dr. Laila. Yeah, Dr. Lailatul Komaria ST, the topic is controllable silica particle for various application. Affiliation ITS Applied Undergraduate Program, Department of Industrial Chemical Engineering. Position lecturer of the ITS Industrial Chemical Engineering Department. Educational background, ITS Chemical Engineering for bachelor degree, and also ITS Chemical Engineering for doctoral degree. And this is her research experience: mass transfer mechanism study on supercritical CO2 extraction drugs palm oil based CFD, plant design preparation magnesium cement from dolomite, functionalization of controllable silica particle and its composite via spray method. And she also speaker at international seminar, international conference on chemical process and product engineering, the third international seminar and fundamental and application of chemical engineering, nanoscience and nanotechnology symposium, international symposium of Indonesian chemical engineering, and also regional symposium on chemical engineering. Okay, now please welcome Dr. Laila. Time is yours.
Okay, thank you, Dr. Saidah, for the time and then for the opportunity for having me in this webinar. As also mentioned by Dr. Saidah here, I will present about my research is about the silica particle, is everything about the silica particle here, because this is the last topic, so maybe all of the participants still have so much energy to participate in this session. Let me share my screen before. So my screen already can be seen? Yes.
Yes.
Okay, thank you. The topic here is about the controllable characteristic silica particles production using spray process. I divide this presentation become 4 section, section 1 until section 4. But for the first, I will speak about the introduction, and then the section 2 is about the controllable silica particles production via a spray method. If we speak about the nanomaterials, the application of the nanomaterial is so much. That is for energy storage, and then for the pigments, electrocatalysts, and then phosphorescence, and then for drugs. So in this whole life, I think we use the nanomaterials. That's why I choose my research in nanomaterials application, because here there is so much application in nanomaterials. And then every device in our life also using the nanomaterials application. So here I can say that the nanomaterials serve as the core of important appliance and device in the daily life. In here, I will focus only on silica particles. So before I continue to the next my speech, I will ask all the participants to answer this question. Did you know the application of silica? You can write your answer in the chat box, maybe. For the participant, can you answer this question? As if you know about the application of silica, as far you know, you can participate in the Zoom chat. I will maybe for 1 minute, maybe. Oh, there is one people says that from Andi, the application of silica, an addictive for manufacture plastic and rubber. Okay, good. And then for another participants. Next, from Aldi Nugroho, he says that the silica for manufacture of fertilizer as moisturizer. Okay, it's good. So many application of silica particles. Come on, from other participants, you can participate in the chat box. Okay, that is 2 person. Thank you for your answer, Mr. Andi and Mr. Aldi. Thank you for answering this question. Yes, it's true. So many application of silica particles. Sorry. Okay. Now, this is some application of silica particles. Here, I already synthesized some of the morphology of the silica particles. Here, there is dense particles, and then dense donut particles, and then hollow silica particles. All of these all of this material is a silica particle, but with different morphology. So here, I just want to show you that the different morphology will obtain a different application. For example, for dense material, for dense silica material, it can be applied as the pigments, or for the in the industry to produce the pigment, and then also for the dense donut particles. Then the dense donut silica particle we can use at the drug delivery, and then for hollow silica particle we can use this particle for maybe for UV protection, but it can be also for the applied for the dense for the drug delivery. So many application of the silica particle. So here, if we can change the structure of the silica particle, here we can attain a high surface area and an optimal morphology for the best fit with certain application. But also here, it depends on our need. If we want to make silica particle for drug delivery, so we can structurize the silica particle, become a dense donut particle, and then maybe for the other application, such as for UV protector, and then we can structurize the silica particles, become the hollow morphology. Here, I will focus the structuration of the silica particles using also the spray process. Just one process, no the other process. Actually, there are so many kind of the structuration of the silica particles or another particles. We can use the sol gel method, and then we can also use the hydrothermal method and the other method. But here, I will focus on the spray process. So in the spray process, the particles initially, which we change the liquid, become the droplets, and then the droplet here undergo the solvent evaporation, and then it depends on the surface precipitation. Different kind of the surface precipitation, it will resulting a different sorry, maybe the participant can mute your audio. Okay, thank you. If the different surface precipitation occur, so we can obtain a different particle morphology. That is dense particle, hollow particle, broken particle, and then the nanoparticle. Nanoparticle is the particle which the size is around 10 nanometer and until 100 nanometer. Here, to structurize the silica particles, here we need the spray precursor, or we can say as the host particles. Here, I use the silica particles, but mostly in this, in my research, I only use the water glass as the silica source, because this is the most not expensive materials, and then the abundant resource of the water glass, comparing with the other source such as Thios or Timos. This is an expensive silica source. And then for the spray process, we need the ultrasonic nebulizer to produce the droplet, because this is the important part in the spray process. We need this. This is the ultrasonic nebulizer to produce the droplet. And then if we use ultrasonic nebulizer, we can produce an uncharged droplet. But if we want to produce a charged droplet, we can use electrospray process. I also discuss in this topic, I also use these two methods using the electrospray and then the ultrasonic nebulizer. This is some kind of the device that I use here. If we use the ultrasonic nebulizer, we can use here using tubular furnace spray drying. These two devices for uncharged droplet, and then for the charged droplet, we can use the electrospray process. For the uncharged droplet, here the ultrasonic nebulizer to produce the droplet. And then the first precursor here, the silica particles. So we need to produce the colloid of the silica particle first before we further process to the tubular furnace. So we pump this silica we pump the colloidal silica to the ultrasonic nebulizer, and then in this ultrasonic nebulizer, the droplet was produced, and then the droplet was carried by the carrier gas using an environmental gas, carried the droplet to the tubular furnace. Here, we can change the temperature, maybe some kind of temperature from 200 degrees Celsius until 1000 degrees Celsius. Here we can vary the temperature, and then after droplet dry and then was catch up by the electrostatic precipitator using high voltage. So the particles was trapped here, and then the carrier gas was waste to the environmental. And then the same kind of the tubular furnace spray drying, we can also use the fire. If here I use the electric heating, so in this kind of in this kind of the spray drying, I use fire to evaporate the solvent. So it's same here. There is an ultrasonic nebulizer, and then also there is a carrier gas. But the different thing is the heating method. In here, we use the tubular furnace or electric heater. In here, we use the fire by using the fuel and oxidizer using the oxygen. The same kind, after the droplet was dry and then was catch up in this electrostatic precipitator, and then the carrier gas was waste to the environmental. For the electrospray, if we want to charge the droplet, so we can use this electrospray method, because the different thing is in the droplet production. If this in this one we use ultrasonic nebulizer, in this electrospray method we use a searing pump to produce the droplet. There is a searing pump here. The precursor is in this searing, and then in the searing we use a high voltage to produce the droplet, and then after that we can collect the produced particle. That's the difference between the electrospray and the spray drying conventional. This is the result of the silica particle after produced using the spray drying. There is some kind of the morphological silica particle that I have been produced. For the first is the dense silica particles. Here I use the spray drying with the tubular furnace, this one. So I can produce the dense silica particles here. I variate the concentration here sorry, I forget adjusting the solution pH. So the colloidal precursor, I just adjust the solution pH from 8 to 11. So as we can see here, all of the particle produced is the dense silica particles with different particle size. And then how about the crystalline of the silica particle? Because the silica is an amorph materials, so there is a significant peak in the XRD result because the silica is just an amorph material, because this is just only silica and there is composite here. And then how about the FTIR result? It's also confirmed that the silica particle was successfully produced, because there is a significant peak at around 1071 here. So this is the silica particles. Okay. And then if I adjust the concentration of the precursor, here I use the concentration from 0.3 until 0.1 mole per liter. So uniquely here, we can produce a donut-like particle. So you can imagine that this is a donut that we can eat, because this is the particles it cannot eat by us. So this is the interesting part why I very interesting in the nanoparticle production, because we just adjust the solution pH, we can get a dense particle, and then after we adjust the concentration, we can get the different morphology. It's so unique to play with the nanomaterials. So maybe if you interesting in the nanomaterials topic, maybe we can collaborate in the research, maybe in the next future. And then how about if we adjust the flow rate of the carrier gas? So here we can get the donut-like particles, but the diameter of the donut particle is so big if we increase the rate of the flow rate. So this is I give the particle formation mechanism if we increase the flow rate of the carrier gas. If we use low gas flow rate, so this flow rate cannot press the droplet, so the dense the spherical particle obtained. But if we use the high gas flow rate, this high gas flow rate will press the droplet, so the droplet will become deformed. The center of the droplet will deform, and then the donut-like particles, like in this SEM image, can be obtained. So this is the particle formation mechanism if we change or we adjust the flow rate from here. I use 2 liters per minute until 6 liters per minute. Maybe if we increase again the flow rate of this carrier gas, the diameter of this hole maybe will be wider than this one. I just try until 6 liters per minute. Here I also change the it is the same flow rate, but I use the other spray dryer method using the burner, using fire. It also has the same particles morphology. Also here, if we increase the flow rate, the donut-like particles here produce. And then if we increase until 6 liters per minute, the hole here become wider comparing to the 2 liter per minute flow rate. Here we just get the spherical with dense morphology. Here, if the previous slide is about the silica particle with dense morphology, and then in this part I will explain about the hollow silica particles. It's a little bit different with the previous dense particles, because if we want to produce a hollow silica particle, we need a template. A template here that I use is the zinc oxide here. Zinc oxide here, I use the zinc oxide resource from the zinc acetate that I use for the template. Now, and then to produce the hollow silica, I adjust the ratio of the zinc oxide and silica particles here from 2.0 until 0.25. So more silica particles. So here we can see if there is a little amount of the silica particles, there is not enough to cover the, if you can see here, there is a big particles here, and then at the surface there is a small particles. The big particles here is the zinc oxide particles, and then the small particles here is the silica particles. So I increase the amount of the silica particles from the ratio of 2 until 0.25. So if we can, you can see here, if we add the amount of this or add the concentration of the silica particles, the zinc oxide particles here more covered by the silica particles. You can see here, and then if we increase again the concentration of the amount of the silica particles, all of the surface of the zinc oxide particles can be perfectly covered by the silica particles. And then the last here, there is small size of the particle. This is the silica particles, and then now we cannot see the zinc oxide particle because the zinc oxide particle surface already perfectly covered by the silica particles. If we can see the if we use TM, another characterization to understand. So this is the black here, the black part here is the zinc oxide particles, and then the outside here, more clear, is the silica particles, the small size here. So we cannot see the silica particles here because there is not enough, the amount of the silica particles is not enough to cover the surface of the zinc oxide particle. This one we can see here, the black part here is the zinc oxide particle already perfectly covered by the silica particles. The transparent one here is the silica particles. We can confirm that this is already covered or not by using the TM, because SEM just only can see the surface, but the inner part of the particle we cannot see. So we can analyze using the TM. This one, how to remove, because here I want to synthesize the hollow silica particles. So I need to remove the zinc oxide that in the inner part of the composite particle. So here I use the hydrogen chloride solution in the concentration of 0.1 molar to remove the zinc oxide particles. So we can see here. The solution become changed from the turbid and then become clear. It shows that the zinc oxide particle already removed from the inner of the composite particles, because the silica particles is the transparent one. So in if we put in this solution, the solution here consists of the silica particles, but the zinc oxide particles are already gone. So this is after zinc oxide removal. There is no big particle size here, only the small size, because the zinc oxide already removed from the particles. So maybe from the clear one using the TEM, this is only, there is no big particle size, which so that there is zinc oxide here, only the silica particles, because this particle is transparent, more transparent than zinc oxide particles. This one. If we compare the previous slide, before the zinc oxide particle is not removed, and then after we remove the particles, there is no black part here, because the zinc oxide already removed from the particles. So here we can obtain the hollow silica particles. So this is only the silica particles. This is the hollow spherical formation mechanism. So if there is a low amount of the silica particles, in the inner part is the zinc oxide particles, the green one, and then the red color here is the silica particles. So if the small amount of the silica particles, so the surface of the zinc oxide is not perfectly covered, and then if we increase the if we increase the silica amount, so the zinc oxide will be perfectly covered here. And then after removal, we just also get the silica particles only. And then for this one is the spherical hollow silica particles. Another particles, I also synthesize the hollow plate silica particles, which the morphology is like here. If the spherical particles like a ball, and then for the plates, the diameter here is so little, is not as big as these spherical particles. This one. So as the same method as before, I also use zinc oxide template, which the morphology of the zinc oxide is like an hexagonal with 6 part here. The same method. I use the different concentration of the silica particles to perfectly cover the zinc oxide particles. So this is the zinc oxide template, and then after the silica addition, we can get the core shell. Here, the black part is the zinc oxide, and then the outer part here is the silica particles. And then I also remove the zinc oxide using the same method, using the hydrogen chloride solution, and then we can get the hollow plate silica particles. This is the last section of this presentation. After I synthesize some kind of the silica particle, which are dense particle, donut-like particles, and then for the hollow spherical particle, and the last is the hollow plate silica particles. And then how about the functionalization or the application of these particles? So for the hollow particles, we can use this one for the UV transparent materials, that we can, these materials can penetrate is around 60% until 80% for UVA and UVB, and then for the visible light, it can penetrate is around 80%. So I check the transmittance for these particles is around 60% and 80%. How about the hollow plate particles? Is perfectly can penetrate all of the visible light and then the UVA light until 100%. Is so it's so good for these materials. And then this is the summary for this topic. I have some kind of particles. There is 4 kind of particles, which different kind application. For dense spherical, we can use this one for the pigment and then for the absorbent. And then for the donut-like particles, we can applicate this one for the drug delivery, and then for the hollow spherical, we can use this one for maybe for photocatalyst, and then for the hollow plate, here we can use as the materials in solar cell. So this is only for the energy application. Okay, maybe that's it from me. That's my explanation about the silica structurization. Maybe thank you for your participation in this topic. I give back to the moderator.
Okay, thank you, Dr. Laila, for your great presentation. Now we come to discussion, question and answer session. So please, all participants, you can raise your hand or just write down your question in the chat room. Any question? Yes, from Aldi Nugroho.
Okay, thank
What is
you.
your question?
Okay, Dr. Laila, I want to ask you, why do you use
Aldi Nugroho.
Okay.
I cannot hear your voice.
Oh, no. Hello.
Can you repeat?
Okay. I want to ask you, Dr. Laila. The first, why do you use hydrogen chloride to remove zinc oxide, not another acid solution? And then, can we change the morphology of the particle? Are there certain about the condition? Thank you.
Okay, for the first question is about how to remove the zinc oxide. Why I use the hydrochloride? Because the zinc oxide particles is dissolved in hydrogen chloride. So this is why I use the template using zinc oxide, because the zinc oxide is can be removed easily just using the hydrogen chloride with the lower concentration, so we can remove the zinc oxide particles. actually I can use another template, but we need another acid, the harmful acid, maybe hydrogen fluoride, but hydrogen fluoride is a dangerous solution. So I use the more safe, than hydrogen fluoride. So I use the zinc oxide template because this is easily removed from the composite, so we can produce the hollow silica particles. And then for the next question, maybe can you repeat the question?
Okay. My question: can we change the morphology of all particles? Are there certain conditions?
Okay. How we can change the morphology of this is for what kind of the silica particles? Is there for the dense particles or hollow particles?
The dense particle.
Or the dense particles.
Yep.
Yes, for the dense particles, we can change in this method. In the spray drying method, we can change the morphology of the particle by change the concentration of the precursor, and then if we this is for the in the precursor, also we can change the pH of the precursor, and then in the spray drying we can change this one. We can change the temperature, so the morphology will be changed, and then also we can change the carrier gas here. This is applicable not only for the silica particles, another particles also can be tuned the morphology by change this operation condition. Maybe you want to synthesize the Ag nitrate particles. Maybe you can synthesize another particles, but for another particle will give different morphology, because this depend on the characteristic of the particles. So maybe in silica particles we can obtain donut-like particles. In the other particles, maybe we can get another morphology. So it depends on the characteristics of these particles.
Thank you very much, Dr. Laila.
Okay.
Yeah. Okay. Aldi, do you have any question again, or it's enough?
Enough. Thank you.
Okay. There is one question from Dr. Eva.
Okay, thank you for the opportunity to ask. Dr. Laila, maybe this is the simple question because it's not my topic. I'm not understand at all. I would like to know, because you say there are different shape of the particles, such as donuts, hollow, and also spherical. In what application they applicate, and for this, for example, the spherical, what is the optimum diameters to be achieved for your experiment in the applications? And can you explain what kind of application you already study in your silica particles? That's all.
Okay, thank you for the good question. Sorry, here. So I have a summary of this structuration of the silica particles. I have a dense particle here. Dense particle is already applicable for the pigment or absorbent, why it can be applied for the pigment, because it's just dense spherical, and then for the donut-like particle, we can use this morphology or these particles for the drug delivery, because this particle have a hole in this part, so this hole can carry drug materials into that penetrate to our body. And then for the hollow sphericals, and then for an hollow plate particle, we already applied for this as the solar cell materials. Why it can be used for solar cell material? Because I already checked that this material can the transparency of these materials is around 99% until 100% for UVA and visible light. So it is good for the application in the solar cell. And then how about the diameter or the optimum diameter of this particle produced from the spray drying method? Maybe it depends on what kind of application that you want to apply these materials. If you want to apply this material for pigment or absorbent, for example, so we need high surface area. So we need a smaller particle size, because we need high surface area to absorb materials. It also applicable for pigment. Also, we need the small particles diameter. How about the diameter that I already synthesized? Here I already this one. For the particle size is around 100 nanometer, 155 until the highest diameter is around 255. So it is good for the application in the pigment material and then for the absorbent materials. So if we want another application, maybe for the cosmetic materials, so we need higher diameter of particle, because if the particle is too small, the particle will penetrate to our body, so it is not good for our healthy. That's from me. Is there any question, Dr. Eva?
Once again, regarding the drug delivery donut form, yeah, the formation. Yes. Can you show me? Yeah, this one. Is it depend if we want to make it the drug release, slow release for drug delivery? How much the size or the hole is depend on the slow release or the size of the diameter, because there are two size, as you know, for donut is the spherical and the pore inside the donut.
Okay.
What should we control? The size of the pore or the thickness of the spherical of the donut size?
Okay, I get the question. It's a good question, I think. The drug materials will put in this one, in the whole in this part.
Yeah.
So if we need slow release of the drug, so the outer part, the thickness of the outer part, maybe we don't need a higher size of the outer part, but if we want to slow release of the drug, so we need a thicker part of this part. So it depends on the outer diameter of the donut particle, not depends on the this hole.
Oh, okay.
Yes.
So that's mean the thickness is affect to the application for the slow release or high release content of the drug delivery.
Yes.
Okay. I get it. Thank you, Dr. Laila.
Okay, thank you.
Okay. There is one question from Andi Setiopati.
Dr. Lailatul, I want to ask, in this study, you are focused on spray method. You also mentioned that there are also another method for this study. For example, salt gel method. I'm just curious why you choose this method. Is there are any advantage of this method comparing with other methods? Thank you.
Okay, a good question from Mr. Andy. Yes, there is so much method that we can use to produce the nanomaterials particles, not only for the silica particles. I mentioned about the sol gel method, comparing with the spray drying method here. In spray drying method, we can produce the particles only in several minutes or maybe in several seconds. Because after, maybe if we use high flow rate of the carrier gas, so the waktu tinggal, what is mean waktu tinggal? The resident time, yes, the resident time of the droplet in this tubular furnace will also maybe in 10 seconds. It depends on the characteristic of this tubular furnace. If we use large tubular furnace, so maybe it will long time. But in general, the residence time of the droplet in this tubular furnace is around maybe 20 seconds or 25 seconds. It's very fast. So we can produce the particles with a high purity in just several seconds. So if we compare with the sol gel method, in sol gel method, we need to stir the particles for maybe 2 hours, and then we need to heat the particles in the furnace for maybe 3 hours or maybe 4 hours. It's very long time comparing with this method, with this spray drying method. All of the spray drying method can produce the particle in just very fast time, maybe just in 20 second time. It's just for me. Is there any question, Mr. Andy?
Dr. Laila, thank you very much.
Okay, is there any question from other participants? Okay, finally, I think it's enough for the last session. I would like to say thanks again for all speakers and all of audience for participation. And before I give to our MC, I will make a conclusion of this lecture today from Dr. Laila. So nanoparticle serves as the core of important appliances and devices in the daily life. Structuration is performed to attain a high surface area and an optimum morphology for the best fit with certain applications. For silica particle application in dense spherical, it can be used as pigment absorbent. For example, in donut-like, it can be used as drug delivery. In hollow spherical form, it can be applied as photocatalyst, and also in hollow plate, it can be applied as solar cell. So silica particle can be applied in industry, healthcare, environment, and also energy fields, depend on the size, morphology, and structure of the silica. Okay, hopefully this guest lecture today will give benefit for us. Thank you for your attention. See you later in the next guest lecture, inshallah. And next turn, I will give back to our MC, Ms. Hilma.
All right, thank you so much for the amazing presentation, Mrs. Lailatul and Mrs. Eva. And before we end the session, let us take picture together to remember this moment. And I will invite all the participants to open up their camera and use the virtual background to take the picture together. And maybe I will wait 1 minute until 4:15. Once again, I invite all the participants to open up their camera because we want to take the picture together to remember this moment. All right, it's already 4:15. I will take the picture in my count. 1, 2, 3, cheese. Okay, once again. 1, 2, 3. Okay, thank you everyone. And as a saying goes, to every beginning there is an ending, and now the event has come to its end. Once again, thank you everyone for gracing our ceremony with your presence. We truly appreciate it. And on the behalf of the organizing committees, I would like to apologize if we have done any mistake throughout the event. I will end my duty now as Master of Ceremony today's event with Wassalamualaikum warahmatullahi wabarakatuh. Thank you.